Hey, what's up everybody? This is Mr. Piercy, and this video is going to be about using L'Hopital's rule to find the limit of functions that would normally produce something referred to as an indeterminate form. But this video and the material that you're going to see in it is going to be specifically for things that you would see in a BC curriculum or a Cal 2 curriculum rather than AB or Cal 1. So in AB, what they show you is that you see two types of indeterminate forms. Now you first get introduced to the idea of what L'Hopital's rule is. You get just a little smidgen of information when we talk about limits at the very beginning of any calculus curriculum. But it's not until after we get a good amount of derivative practice under our belt do we revisit the idea of L'Hopital's rule, so that way we can uh, use the derivatives of the function expressions that we have to help us evaluate the limit whenever we wind up with an indeterminate form, like what you're seeing on the screen. So here's a couple of examples of things that you would have seen where in this case, if we do direct substitution with the 3, we're going to wind up with a 0 over a 0. And if we did the substitution of infinity directly into the bottom rational function, then that would give you infinity over infinity. So two examples where we would have to use L'Hopital's rule in order to take the derivative, in order to actually take the derivative of the parts to be able to evaluate the limit appropriately. Okay. And here when it's telling you problems arise, we take the limits of each situation. Some think that 0 over 0, and golly, I really hate when math people say this. It cancels out, where they say, oh, this over this cancels. And no, it simplifies to be 1. But in this case, 0 over 0 does not simplify to have a limit of 1. That's what we refer to as our indeterminate form. Well, there's more than one type of indeterminate form. AB calculus introduces you to two, 0 over 0 and infinity over infinity. Well, what the rest of that stuff is talking about is that there's really there's 5 more types of indeterminate forms that you need to be aware of, so that way you can perform L'Hopital's rule correctly when you encounter them. So for an example like this, it's like, normally we say any number multiplied by 0 is 0, but what about 0 multiplied by infinity? Well, what does that do? Well, that's called the indeterminate form, because remember, infinity isn't a real number. It's a concept. It's an idea. So for what we're seeing whenever we have something like this, where it is going to be 0 multiplied by a positive or negative infinity, what we're going to end up doing is we'll take our function, whatever it is, and we're going to kind of write it as a ratio of 1 over f of x. And that is how we would set up L'Hopital's rule in order to work with that particular indeterminate form. The next one that is here in the middle, infinity minus infinity. Again, infinity is not a real value. It's a construct. It's an idea. So what we would do here is what we would look at here is we would try to get my thoughts correctly. Convert to a fraction version of the indeterminate form. Where you would say like infinity over infinity. So that way you could start doing the derivative the way that we would have done it in AB Calc. And the last one that we're going to be looking at is really going to kind of be for all of these where we're having something raised to a 0 power, or in the last case, 1 raised to the infinite power. Here, this is what we're going to be looking at for these. We'll say And if you don't want to write this down, you don't need to. I'm just trying to give it in multiple places because you'll see this again. Let y be the function which gives the indeterminate form. And then what we do is we find the limit of the natural log of y. And we'll see some examples that work with that. But so here, these are two examples that I want you to go ahead and work on first. Pause the video, work out the limit for both of these algebraically using L'Hopital's rule, and see what you're able to get. And when you're ready, hit play and check your work with mine. Okay, and how did you do? Here I actually worked the problem out two ways. Let me go ahead and kind of label which ones I did which way. Let me get a color here. So this stuff here, this was just an algebraic approach where I was able to factor the denominator and simplify out the common factor of x minus 3. And this here on the right side in red, that was L'Hopital's rule. And the stuff in green that I'm doing here, this is where we're just using the method to divide out with the largest term in the fraction here. This is my algebraic approach that we're using to simplify the numerator and the denominator, so that way we can get rid of the infinity over infinity situation. And here, if we use L'Hopital's rule, oops, here's my L'Hopital's rule where we had to do it a couple of different times. And one of the things that I forgot to do on the one in red is I really should have written the limit in such a way that I was showing I'm using L'Hopital's rule, where I should have said f prime of, oops, not f prime of g, f prime of x over g prime of x. This is what I need to do to actually show that I'm using L'Hopital's rule, and I forgot that bit here. So anyway, there is your limit using either an algebraic method or the L'Hopital's rule approach. So now, and that's what we would have seen problems similar to that in an AB curriculum. Now here what we're seeing are they're just general strategies for whenever you have a limit in anything that you're being asked to evaluate the limit for. The first thing you should always try to do is just do direct substitution. Just see if plugging in the number will give you the limit that you're looking for. Numerically, you can plug in something close to your number. That would be probably beneficial if you're allowed to use a calculator of some kind to help you with the arithmetic of it. But you could also maybe just look to see, sometimes you'll be able to tell very easily whether it's going to approach a 0 or an infinity or something like that. You could always try graphing the function and see where the limit would approach, remembering the idea of that, for the limit to exist, the left and right hand limits have to match and the function has to be defined, or the left and right sides need to match. Algebraically, you could see, I used an algebraic approach on the last two examples, but sometimes, remember, there's the conjugate thing whenever we have like square roots for our expressions in our numerator or the denominator. And when all else fails, especially if you notice immediately, like if you go direct substitution and you see, oh, hey, look, this is an indeterminate form, a lot of times you might just go from the direct substitution straight to using L'Hopital's rule. So here, they're just kind of giving you some mathy explanations to show you what we're doing for the use of L'Hopital's rule. Um, but I think we can kind of move on from here and see. Let's just go ahead and start getting some of these practice problems in. Here, the important tip when demonstrating L'Hopital's rule applies, you have to write the limits of the numerator and the denominator separately. Okay, you have to actually show something that you're doing for L'Hopital's rule. Okay, that's why I wanted to kind of show that I was, when I said the limit as x approached some number. Okay, if I'm using L'Hopital's rule, I want to in some way indicate that I'm taking the limit or the derivative of the numerator and the derivative of the denominator separately, and then actually do the derivatives in the numerator and the denominator, whatever they work out to be. So here is our first example of of a limit that we're going to be looking at. Now, just don't get into the mindset that everything that you're going to be looking at is going to be L'Hopital's rule. It's just a limit. Okay. Now we can see that if you plug in the 1 in for x, the natural log of 1 is a 0. And if you plug in a 0 here, that's going to give you 0 over 0. So that is our indeterminate form. So it's pretty obvious here that we're going to be doing L'Hopital's rule. So if I just do direct substitution here, I'm going to wind up with the indeterminate form of 0 over 0. So this is how I'm going to show my work here. I'm going to say the limit as x approaches 1 in this case, and I'm going to say the derivative of the numerator over the derivative of the denominator, and we'll just do the derivative. So the derivative of natural log of x is going to be 1 over x, and the derivative of x minus 1 is going to be 1. So now, if I do my substitution, we're going to get 1 over 1 over 1, which just simplifies to be 1. So there's the limit of this first problem. Moving on to this next one here, if I try to do direct substitution again, well, cosine of 0 is 1. 3 times 0 is 0. So this would give me a 1, this would give me a 0, and this would give me a negative 1, giving me a 0 in the numerator, and 4 times 0 in the denominator, 0 over 0. So we have another indeterminate form with this limit. And we see that by just doing our the direct substitution. So again, I'm going to show that I'm going to do the limit as x approaches 0 in this case, where I'm going to specify I'm taking the derivative of the numerator and the derivative of the denominator, f prime of x over g prime of x, and start taking the derivatives. So the derivative of the numerator, the derivative of cosine will be negative sine of x. The derivative of 3x would just be a 3. The derivative of the negative 1 is 0, so we don't need to write that. And the derivative of the denominator is 4. And now we could try doing our direct substitution. So if I say negative sine of 0 plus 3 over 4, well, sine of 0, positive or negative, this goes to 0. So I'm left with just 3/4. And there's the limit for that one. Now, What I would like you to do is go ahead and see if you can pause the video and work this one out in advance of me, and just see if you're able to kind of follow along with what we're doing with L'Hopital's rule. Go ahead and try working this one out, and when you're done, press play again and see how your work and my work compare. All right, so here's an example that the limit of this particular function as x approaches infinity is infinity. And we did have to use L'Hopital's rule twice. The derivative of e to the x over x squared will give me e to the x over 2x, but that also gave me the indeterminate form, so I had to do L'Hopital's rule again. So the derivative, the second derivative gave me e to the x over 2, and at that point we can do the substitution. E to the infinite power is infinity, so infinity over 2 is, we just say it's infinity. And here is the next example that, again, I would like you to pause the video and work this one out and see how your work and my work compare. All right, here's example number 5. And the reason why I'm asking you guys to try these is because these are all very basic L'Hopital's rule stuff that you would have seen in an AB course material. But here we wind up getting a limit of 4/3. Just doing direct substitution at the beginning shows we have infinity over infinity. Take the derivative of both the numerator and the denominator, and I get 4 minus e to the negative x power when I use the chain rule on e to the negative x. And if I do direct substitution, e to the negative x power becomes e to the negative infinity power, which is basically, 1 over e to the infinite power, so 1 over infinity is 0. And we're left with just 4/3. So there's the limit. And this is the next one. Again, I want you to go ahead and try working this one out on your own using just kind of your normal derivative or limit stuff here. See what you wind up with. When you're ready, hit play and check your work with mine. All right. Here, this one did not require any particular things other than understanding your unit circle. Doing direct substitution in this case does not produce infinity over infinity. Sine of pi will be 0 in the numerator, and cosine of pi will give me a -1 in the denominator. So I do have 0 over a +2 in this case when I do direct substitution. So 0 divided by 2 in this case gives me a limit of 0. And here's the last one that I want you to try working independently for now. So go ahead and pause the video on this one and try finding the limit of this particular function. And when you're ready, hit play and check your work with mine. All right, and how did you do on this last one? Direct substitution produces the indeterminate form of infinity over infinity. So I show I'm going to use L'Hopital's rule, take the derivative of the numerator and the denominator, giving me 1 over x divided by 1 over 2 radical x, multiply by 2 radical x to both the top and bottom parts of the fraction to simplify it, giving me 2 radical x over x. And I wrote it out in exponential form, so it's a little easier to see how the x term is going to simplify out of the numerator with properties of exponents, giving me 2 over the square root of x, or 2 over x to the 1/2 power, however you prefer it. But at that point, when you do substitution, you get 2 over infinity, which would simplify it to be a limit of 0. So a lot of that stuff, again, really not anything new for things that we've been doing with L'Hopital's rule. But now we're going to start seeing some different types of indeterminate forms where maybe we're going to get something that says infinity times 0 or something along those lines. And here what it's kind of showing you to do in that situation, what we're going to do is we're going to take the product of whatever the two pieces of the function happen to be, f and g of x, and we're going to write them in some ratio like that, okay? And then we would be able to start to apply L'Hopital's rule. So let's take a look at this first one here. If I were to do direct substitution, in this case, substituting the 0 for x, I would get 0, and then I would say times the natural log of 0, which would in this case give you 0 times negative infinity, because we're approaching 0 from the right side of the graph. So remember, your logarithm function is going to do one of these things. So as you approach 0 from the right side, you head down towards negative infinity. So that's how we get the 0 times negative infinity expression here. So let me clean this up just a bit. So this gives you the indeterminate form of 0 times negative infinity. Okay. So what that tells you to do, it says take your function and write it as a ratio of one function over the reciprocal of the other function. And in this case, the reciprocal of the other function that's going to be easier to do is going to be the x term. I think that one's going to be a little bit easier to work with, taking the reciprocal of. So here what I'm going to do is I'm going to say the limit as x approaches 0 from the right side of the function. And what I'm going to do is I'm going to say, let's see, how do I want to think of it as? We can think of this one here as f, and we can think of this function here as g if we need to classify anything. So here I'm going to say g of x over 1 over f of x. And that is what we're going to do to indicate that we're using L'Hopital's rule now. So what I'm going to get here is I'm going to just say the limit, and I'm going to just, before I actually do the derivatives, I'm going to just rewrite it. So I have the natural log of x over 1 over x. Okay. Now I'll go ahead and start taking the derivatives. So the derivative of the natural log of x is going to be 1 over x. The derivative of 1 over x, in that case, is going to be a negative 1 over x squared. And then you can start doing substitution here. If you start plugging in 0, in this case, you're still going to wind up with something that doesn't work very well. But we can simplify this particular ratio by multiplying, kind of like what we did earlier, multiply by the reciprocal of the denominator. So I can multiply here by negative x squared and multiply here by negative x squared. And these are going to simplify to be 1. And I'm going to be left with a negative x by itself. So now you can substitute the 0 in there. So as you approach 0, plugging in 0 or anything close to 0, in this case is going to give me a limit of 0. Moving on to the next example here, you can see that in this case, if you were to look at, here we can think of this, again, I'm going to think of this as function f, and all of this is function g for the product of the two functions that we have, or the two expressions that we have. And if I were to do direct substitution here, I'm going to wind up with infinity times 0, which is one of our indeterminate forms. So to show that I'm going to do L'Hopital's rule here, again, we're going to say the limit as x approaches infinity. And in this case, I'm going to do the same thing like I did on the last one. I think 1 over x, I think the f, just the x, is going to be the easier one to do the reciprocal of. So here I'm going to say g of x over 1 over f of x. And I'm not going to do any derivatives yet. I'm going to just write it in that form. So I'm going to say e to the 1 over x power minus 1 divided by 1 over x. Okay. So now here, if you try to do the indeterminate form, you're going to wind up with 0 over 0. Okay, and that's what's, again, hey, L'Hopital's rule, get going. Okay, so the derivative of the numerator, when we look at that, using the chain rule on the e to the 1 over x power is going to give me e to the 1 over x power times 1 over negative x squared. And if I take the derivative of the denominator, I wind up with a 1 over negative x squared. So in this case, by doing L'Hopital's rule, we're going to have an expression that would simplify to be 1, leaving me e to the 1 over x power by itself. So if you plug in infinity into there, you're going to wind up with e to the 0 power, which would be 1. So hopefully things are going okay so far. But here we're going to be moving on to some new types of limits. Instead of taking the product here, now we're going to look at the limits of a difference, where we might wind up with, like is showing you up at the top of the screen, infinity minus infinity. And so what it tells you to do in this case, it says change this into a quotient or a product. A quotient or a product. By writing the difference between the two fractions and getting a common denominator to collect like terms. Okay. And we see here, step 1, write the difference of the two quotients as a product or a quotient, apply L'Hopital's rule or some other method to the indeterminate form, and evaluate and see what you're able to get. So here, straight away, if we substitute 0 into the expression here, we're going to wind up with something that says infinity minus infinity. Now, taking a look at the expressions, what we're going to do here is we're going to rewrite it as, in this case, I'm going to rewrite it as a quotient. Okay, so I'm going to say the limit as x approaches 0 from the right-hand side. In this case, will be, excuse me, we're just kind of, essentially we're just putting everything as a common denominator, okay? So take everything that we have in the parentheses already and just rewrite it as a common denominator. And if I do, I'm going to wind up with x minus e to the x power minus 1 divided by x times e to the x minus 1. And again, if I do my substitution here, I'm going to wind up with the indeterminate form of 0 over 0. So now this is where it's going to say take the limit of either a product or a quotient. So here I'm going to start doing my L'Hopital stuff. X approaches 0 from the right side. And in this case, we're going to say, how do I want to say this? I think in this case, we're still going to, let's see. I think the easiest way of expressing this one would just be to say the actual limit of the numerator, x minus e to the x power minus 1, over, oops, not there, over the limit as x approach 0 from the right-hand side of the denominator, x times e to the x power minus 1. And so now we're going to take the derivative, or look here and see what we get for, taking the derivative of both sides in this case. And here, I'm going to get the derivative of the numerator will be 1 minus e to the x power. The derivative of the denominator, if you distribute the x here, you're going to get x times e to the x power minus x. No, I think I wrote the denominator wrong. Yeah, let's get rid of these parentheses. I think I messed up on my denominator. So let me just fix that real quick. There we go, just like that. So now, if I take the derivative of the denominator using the product rule on x times e to the x, we're going to wind up with x times e to the x power plus e to the x minus a 1. Nope. Nope. Golly. I wish I could pause and rewind this thing, but I can't. So what did I mess up on? I'm still messing up on my common denominator. So that would be x times e to the x minus x. There we go. Golly. Minus x. Now we're firing on all cylinders. So now I have my derivative correct. Okay, sorry about the mix-up on my common denominator there. All right. So doing substitution here, in this case, will again result in an indeterminate form of 0 over 0. So we have to keep using L'Hopital's rule here. And the derivative of the numerator, in this case, would just be negative e to the x power. The derivative of the denominator is going to work out to be x times e to the x power plus e to the x power plus e to the x power again. And here, we're going to be able to combine our like terms, e to the x power. And I'm going to say negative e to the x power over x times e to the x power plus 2 e to the x power. And in this case, now, if I substitute 0 here, I'm going to get negative 1 in the numerator over 0 plus 2 times 1, which would be a 2. So this one will work out to be a limit of negative 1/2. So, common denominator mix-up aside, let's move on and try one more and see how we're doing. So here again we have the difference of two expressions, secant of x minus tangent of x. And personally, I like to, whenever it's reasonable to do so, I prefer to look at any trig expressions in terms of sine and cosine. So if I rewrite this in terms of sine and cosine, that's going to be the limit as x approaches pi over 2 of 1 over cosine of x minus tangent will give me, oh, don't know why I'm saying equal to, minus sine of x over cosine of x. And we can look at that in terms of a common denominator also. They actually have a common denominator, so I don't have to do anything to it, and I can just keep going here and say that would be 1 minus sine of x over cosine of x. So here, we're going to wind up with something, unfortunately, that doesn't work. If I do my now, starting at the very beginning, if I just do my substitution directly into this is going to give me infinity minus infinity. And the simplified expression that I have at the end on the right side, if I substitute the pi over 2 here, that's going to give me a 0 over a 0. So either way, we understand that we're doing L'Hopital's rule here. And so now what we're going to do is we're going to take the limit of I think in this case, we'll just take the limit of the numerator and the denominator by themselves. And so I'll say the limit as x approaches pi over 2 of, in this case, what I have on the right, f prime of x over g prime of x. So the limit of 1 minus sine of x will be a negative cosine of x. And the derivative of cosine will give me a negative sine of x. So now if I do my, try my substitution here, pi over 2, negative, or cosine of pi over 2, in that case is 0. It doesn't negative really doesn't matter. And negative sine of pi over 2 is going to be a negative 1. So we no longer have the indeterminate form, so 0 divided by negative 1 is 0. And there's your limit for that expression. So now here we're going to be taking a look at the last 3 types of indeterminate forms where you say 0 to the 0 power, infinity to the 0 power, or 1 to infinity. Okay, what it's telling you to do, it says let y equal f of x to the g of x power, whatever that is. Take the natural log of both sides and then try to evaluate it. Now the one thing you got to be careful of here is that a lot of times when you're done working out the majority of the work here, you're left with your limit in terms of the natural log of y. So you don't want the limit of the natural log of y, you want the limit of y. So let's take a look here and see what we end up with. Now this one by itself, ideally, this should be familiar to most of you. That is the expression that generates E. That was the expression for the compounding interest that we do to find where that number E came to be in to begin with. So, sometimes you see it with n's here instead of x's, okay? But either way, we wind up with the same value of E. So ideally, when we're done, we know in advance, because of this is a very popular expression in mathematics, we should know the limit is going to be E in this case before we even get there. Okay. So here, if you just do direct substitution, you're going to wind up essentially with something over infinity, where you're going to wind up with 1 over infinity when we do our direct substitution here. So this is how we're going to take a look at this to resolve it. Actually, that doesn't. Do you wind up with 1 over? Yeah, you do wind up with 1 over infinity. So, but we know that 1 over infinity in this case is not going to give me the limit of 0. It's definitely going to give me a limit of E. So let's see what we have here. This is how I'm going to approach it. I'm going to say let y be equal to that expression of 1 plus 1 over x to the x power. So that means here we'll take the natural log of both sides. So we'll say natural log of y will equal to the natural log of 1 plus 1 over x to the x power. Properties of logarithms say that I can take this x and move it in front of the expression. So natural log of y is equal to x times natural log of 1 plus 1 over x. And so now you can see that we have kind of that product thing that we would look at. So here, and I really should be writing my limit. I really should say the limit. Nope, not there, not underneath it. I should be saying the limit as y approaches, not y, as x approaches, what was it, infinity in this case. I really should have that limit symbol there. And it really should be legible as x approaches infinity. There we go. Uh, so here, if I do this, we would wind up with infinity times a 0 in that case. And so that means we need to keep working. So I'm going to rewrite this because here we have the product of infinity times 0 or 0 times infinity. This is where we're going to take the ratio of the two functions here. So in this case, what I'm going to do is I'm going to take the limit of both sides. So here I'll say the limit of g of x over 1 over f of x, like we did in some of the other expressions. And so if I do that, that's going to give me 1, nope, the natural log of 1 plus 1 over x over 1 over x. And now we're going to go ahead and start taking the derivative of both the numerator and the denominator for L'Hopital's rule. The numerator, the derivative on this one, we're going to have to use the chain rule. And we're going to wind up with 1 over 1, nope, yes, 1 over 1 plus 1 over x times negative 1 over x squared when we use the chain rule to take the derivative of that. And the derivative of the denominator is going to give me a negative 1 over x squared. And again, we can see that these two expressions, I have a negative 1 over x squared here and a negative 1 over x squared here, and those are both going to simplify to be 1. So I'm left with the limit of the natural log of y as x approaches 0 to be equal to 1 over 1 plus 1 over x. And now we can do our substitution as approaching 0. I'm sorry, approaching infinity. If I do it approaching infinity, I'm going to get 1 over, this is 1 over x. That would be 0, so 1 plus 0. So that just gives me a limit of e. I'm sorry, a limit of 1. Okay, but remember, this is the limit as x approaches infinity of the natural log of y. So if I look at the natural log of y and I convert it from an exponent or from a logarithm to an exponent using your change of base rules, that's going to give you e to the first power to be equal to y. So in this case, we would just say e is equal to y or y is equal to e, however you want to think of it. So again, we knew what the limit was supposed to be begin with, because the expression that we had is a very famous one in mathematics. But now we've shown that yes, the limit of that expression will in fact be e, and go from there. Now this example is a bit intimidating to look at because of the integrand expression, or the integral that we have in the numerator is a definite integral. And one of the things that will make this problem very difficult to work on the at the outset, remember, what are we doing? We're talking about, okay, can I do L'Hopital's rule? Okay, uh, so if you do the direct substitution of the 1 in the denominator, for sure you're going to get a 0. So uh, we need to do something in order to simplify that, so I don't have a 0 in the denominator anymore. But what is L'Hopital's rule asking me to do? We're going to be taking derivatives of things. Well, what is an integral really? It is an antiderivative. So what I'm doing, according to what an integral is and what L'Hopital's rule is I'm going to take the derivative of an antiderivative. Okay, so that's what we're seeing in the numerator here. We're taking the derivative of an antiderivative, which is, in this case, going to refer back to our fundamental theorem of calculus, part 2, where I said the derivative of an antiderivative is equal to f of g of x times g prime of x, the derivative of an antiderivative. So here, the easiest way of expressing that what I'm going to be doing here by using L'Hopital's rule to show that I'm going to be taking the derivatives of both parts of the fraction, in this case I think is to just write the limit of, well, I guess we can, as n approaches 1, I suppose we can still say f prime of, what do we want to write? F prime of g of x. F of x over g prime of x. So the derivative of the antiderivative in the numerator, in this case, will be e to the n squared power times 2n. Okay? So remember, we're taking this upper bound, and it's going to get substituted in here. That's what the f of g of x part is. And the g prime of x is the derivative of the n squared, so that's where I'm getting e to the n squared power times 2n, and the derivative of the denominator is going to be a negative 1. So that is essentially going to give me a negative 2n times e to the n squared power and if we substitute a 1 here, negative 2 times 1 would be negative 2. E to the 1 squared power would just simplify to be a negative 2e. And there's our derivative now, or sorry, not our derivative, but our limit when we can do direct substitution at that point. But again, the key, I think most of this stuff here, probably okay at this point, ideally, hopefully. But if you didn't remember this part up here at the beginning, if you didn't understand what you're seeing in the numerator, you're seeing the derivative of an antiderivative using L'Hopital's rule, then that fundamental theorem of calculus part 2 may have eluded you, but that's really the key to working this particular problem out. Now, this one here is going to be pretty similar to things that we've done already. And if you want to, go ahead and pause the video and work this one out in advance. And this one, you know, it's easy to look up now, I guess, because they're telling you exactly where it came from. It's from the movie Mean Girls. And in this case, if you, again, try to do, you know, direct substitution, cosine of 0 in the denominator is going to give you 1, even if it's squared. So we're going to have our 0 in the denominator. And we would wind up with the limit of natural log of 0 in the numerator, which is undefined. So we're definitely going to need to reevaluate this particular function. And the easiest way of doing it is by using L'Hopital's rule. So here I'm going to say the limit as x approaches 0, and I'm going to find the derivative of the numerator, so f prime of x over g prime of x. Okay, so the derivative of the numerator, in this case, the derivative of 1 minus x is going to give you a negative 1 over 1 minus x. The derivative of sine, in that case, will be a cosine, so minus cosine of x. And in the denominator, we're going to get a, we have to use the chain rule on the cosine. So overall, we get negative 2 cosine of x, and the derivative of cosine will be negative sine, so that works out to be positive 2 cosine of x times the sine of x for the denominator. Okay, and now let's see what happens if I substitute 0 in here. So if I substitute 0 in the numerator, I'm going to get a negative 1 over a 1 minus cosine of 0, in this case is a 1. And so 2 times cosine of 0 is going to be a 1, but the sine of 0 is going to be a 0. So that works out to be negative 2 over 0, which is definitely not an indeterminate form. So in this case, the limit is undefined, or the limit does not exist, however you want to think of it. And here, this is coming up to, I believe, our last example for how we're looking at L'Hopital's rule here. And they're giving it to us in terms of a graph, because we don't necessarily know. I mean, we could create the function for g of x, but it's a piecewise function with 2 line segments and a quarter circle is what it looks like. And so it's asking us to evaluate the limit as x approaches 4. So if you look as x approaches 4, looking at the function g of 4, g of 4 is here to be a 2, so that would give me 2 times 2 minus 4 over sine pi of 4, so sine 2 pi, so that would be 4 pi, so that would be 2 complete intervals on the unit circle. So sine of essentially 4 pi here, that would be 2 complete revolutions. And so, you know, at sine of 0, you're at 0, so you get 0 over 0. So we're using L'Hopital's rule because we have an indeterminate form. And here, because they're using g of x in the function already, I don't want to try to convolute things a little so I'm going to show discretely the limit as x approaches 4 of 2 times g of x minus x over the limit as x approach 4 of sine pi x. So here I'm just showing I'm actually taking the limit of the numerator and the denominator discretely. So the derivative of the numerator in this case would just be 2 times g prime of x minus 1. The derivative of the denominator, we have to use the chain rule because that pi x is inside of the parentheses of sine, so we have to use a chain rule on the denominator, which would give me pi times cosine of pi x. And now we can look to see, okay, well, what if we get a 4 now? So the derivative of g at 4, okay, so let me scroll back up a little bit so you can see the graph. The derivative of g at 4 is basically just the slope of the line. So g prime of 4 in this case is the slope of this line segment here, which looks like it is a 2. So here I would get 2 times 2 minus 1. And cosine of 4 pi in this case, similar to the sine function, that would just be two complete revolutions around the unit circle, once, twice, and we just wind up right here. So cosine of 0, or cosine of 4 pi in this case, is 1, so that would be pi in the denominator. So we wind up with 4 minus 1, 3 over pi. Looks like it's going to be our limit for that particular graph as x approaches 4. Or not the graph itself, but the overall function. And that is going to kind of wrap things up for what we're looking at for the indeterminate form and how L'Hopital's rule is going to use it. Hope you found this informational and helpful, even if lengthy. And if you have any questions, please let me know. Get in touch with me, and I'll be happy to help. Until next time, guys, thanks for watching, and take care, and we'll talk to you soon.